Dear students, in this video, we are going to see subgroups and cyclic group. See the definition for subgroup and this theorem and the definition for cyclic group is given. These three we will see after seeing the examples of a subgroup and cyclic group. This also we will see later. We will discuss later after seeing the examples. Now you see here. Now you see the fourth question. Show that Z6 addition modulo 6 is a cyclic group. Okay. How to prove that cyclic group? What do you mean by cyclic group? You see here, cyclic group means we have to check whether a single element, any element, generates or creates all the elements of the given group. Okay. We know that already Z6 addition modulo 6 is a group. Now we are going to prove that Z6 addition modulo 6 is a cyclic group. Okay. First we list all the elements of Z6, that is 0, 1, 2, 3, 4, 5. Okay. Now here we are going to show the element 1 is generating all the elements of Z6. Okay, that's why here we are putting the notation like this. You see, like this. See, if you put the symbol like this, surrounded by the number, which means this number generates all the elements of Z6. Okay, this is called generator. Okay, the element 1 is a generator. This is the symbol for that. Okay, so now we will check. You see number 1 and then you put here degree 1, which means you write the element 1 time. Okay. Now 1 power 2, you write the element 2 times, but here this power 2 means not multiply the number 1 with 1. No, it's not like that. See here, what is the binary operation? Here binary operation is addition modulo 6. Okay, so that here 1 power 2 means you write the number 1 2 times and apply the binary operation. What is given here? Here the given binary operation is addition modulo 6. So that I write 1 2 times, this 2 times, apply the binary operation addition modulo 6. Okay, now you add 1 and 1, how much? 2. Okay, so 2 is less than 6. So if you apply modulo 6, the remainder is 2. Okay, you see, similarly you can do this. Now you see this one, 1 power 6, which means you write here 1 1 1 1 1 1 6 times, and then in between apply you the given binary operation, that is addition modulo 6. Okay, actually here the answer is 6. Okay, but here you write 6 is equal to 1 multiply your modulo, that because addition modulo is 6, so 1 multiply 6 plus 0. So this answer is here. Understand? In a similar way here they have written, but here the number 5 is less than 6. So if you divide 5 by 6, the remainder is 5. That's why we are writing here 1 2 3 4 5 we are writing, but here 6 we are getting, so that after applying the modulo 6 your answer is 0. Okay, so now you list all the elements. You see 1 2 3 4 5 0, you list all the elements. This list is nothing but equal to your set, your group. So that this is called cyclic group, because this element 1 is creating all the elements through the binary operation, that addition modulo 6. That's why this Z6 addition modulo 6 equal to this. Okay, that's why this is called a cyclic group. Z6 addition modulo 6 is called a cyclic group. Okay, we will see another example. Now you see here, Z6 addition modulo 6 is a cyclic group generated by 5. See, in the previous example we have proved that Z6 addition modulo 6 is generated by 1. Okay, similarly here we are checking it is generated by 5. Okay, now in a similar way you write 5 power 1 means 5. 5 power 2 means you write 5, 5, apply this addition modulo 6 in between. Here 5 power 2 means you write 5 two times, in between you write addition modulo 6. Okay, now 5 plus 5, first you have to add 10. You apply the modulo 6, which means remainder 4. See, I explained here in this example. You see here 5 power 4 means 5, 5, 5, 5. In between you apply addition modulo 6. Okay, now you see here 5, 5, 5, 5, which means 20. So that 20 is equal to 3 multiply 6, because here modulo is 6 and remainder is 2. That's why we are writing this 2 as an answer here. Okay, in another way you can say that you see here 5 power 3, what is the answer we are getting? See, 5 power 2 you are getting 4. So this 5, this 5. So this 5, this 5, your answer is 4. So this 4 and 5 is 9. So you divide by 6, the remainder is 3. Okay. Similarly, see 5 power 3. 5 power 3, answer is 3. So that, see here, 5, 5, 5, 5, answer is 3. So 3 plus 5, how much? See, that's what I'm doing here. 3 plus 5, how much? 8. Okay, see, for first 3 5s, you have answer 3. This is here. Okay, so and then plus you add 5, so 8. Now you do the modulo 6, that is 8 equal to 1 multiply 6 plus what is the remainder? 2. That's why this answer is 2. Either you can check this method or this method. Okay, both is right. Okay, in a similar way you can write until 5 power 6. See what you are getting? 0. Now you list the elements. 5 power 1, what you are getting? 5, 4, 3, 2, 1, 0. You write. So the number 5 generates 5, 4, 3, 2, 1, 0. This is nothing but equal to your set, that is Z6. Okay, therefore Z6 addition modulo 6 is nothing but is 5 generates all these elements through addition modulo 6. This is equal to this. That's why we are telling that Z6 addition modulo 6 is a cyclic group generated by 5. Okay, now you see here another example. In a similar way we can prove that Z7 minus 0 multiplication modulo 7 is a cyclic group. Here binary operation is multiplication modulo 7. Okay, here see they given in the question show that this, but they are not given the element here. See, no element is given. See here, element is given. See, element is given. So you are taking 5 and doing, but here element is not given. But randomly means I chosen 3. Just I'm trying 3 power 1. Just see this. Just I select by trial and error method. We will check. See 3 power 1, 3 power 2, 3 power 3. In a similar way, you write the answer. Okay, for example here I explain for this. Okay, see 3 power 4 means 3, 3, 3, 3. How much is the answer? 81. If you multiply, then 81, see we can write as 11 times 7, because here your binary operation is multiplication modulo 7. So that I multiply first all the 3's, which means 81. Then I see apply the modulo 7, which means 11 multiply 7 plus 4 is equal to 81, which means your remainder is 4 is your answer here. Okay, or you can write this. See, for 3 power 3 your answer is 6. So for these 3 3's you will get 6. So 6 multiply 3 is 18. Again you apply the modulo, that is 2 multiply 7 plus 4. Here the remainder is 4. Either you do like this or do like this. Both way you will get the same answer. Okay, see in a similar way you can write 3 power 5. How much? You do like this, you can find the value. 3 power 6, yes, you can find the value. Now you list all the values. 3, you list all the values. 3, 2, 6, 4, 5, 1. Okay, So here 3, 2, 6, 4, 5, 1. This is equal to nothing but equal to your set. Okay, so what is the set? 1, 2, 3, 4, 5, 6. Okay, so that is z7 minus 0 is equal to this. Okay, that's why we confirm that this number 3 generates all these elements which is equal to the set. Therefore this is the generator. We can confirm that. Therefore z7 minus 0 comma multiplication modulo 7 is a cyclic group, no doubt. Is here, see here. But in this question, show that z7 minus 0 multiplication modulo 7 is a cyclic group generated by 5. Yes, here it is given. You see, the number is given. So no need to choose any number randomly. You have to take this 5 and then you try. See, 5 power 1, 5. 5 power 2 means 5, 5. Apply this multiplication modulo 7. Then what you are getting? See, 5, 5, 25. So 25, which means 25 is equal to 3 multiplied 7 plus 4. So the remainder is 4. So you are writing. Okay. You know that. See how to write this. Okay. Similarly, 5 power 3, you write your answer is 6. 5 power 4. So similarly, you write until 5 power 6. Your answer is 1. Okay. Now you list all 5, 4, 6, 2, 3, 1. See 5, 4, 6, 2, 3, 1. See the number 5 generating all these elements when you apply the binary operation multiplication modulo 7. So that this equal to your set. Okay, because your set is this. See, either 7 minus 0 is nothing but 1, 2, 3, 4, 5, 6. So that this equal to z7 minus 0. Okay, so 5 generates all these elements. So we can conclude that z7 minus 0 is a cyclic group, no doubt. Okay, now you see here, we'll go. That's given in the definition of the cyclic group. You see here, we'll take a finite group G comma star. Okay, and then is called cyclic if and only if every element in G is a non-negative power b power n for some fixed element b. Yes, see, we take some finite group. You see, actually this is the group. Already we know that this is the group. Is that 6 at model of 6? Then you take any element. If that element with any positive degree, if it generates all the elements, then we say that the group is cyclic group. Okay, is that 6 comma model 6 already a group, no doubt, but we are checking the cyclic group. Okay, so by seeing the example in advance, now we understand. So we understand the definition of the cyclic group through the examples. Okay, we understand the definition of the cyclic group through the examples. Okay, now here we have two more questions that's about subgroups. We have two more questions that's about subgroups. Okay, we will see on these example 5 and 6 in the next video. Thank you.